So I'm going to talk about distributed memory and communication, and then a lot of NPI. There are other ways to communicate in distributed memory, but none of them have anywhere near the traction that NPI does with portability. There's things that I won't talk about today, I might mention tomorrow, like SHMEM, and SHMEM is very, very sort of historical and supercomputing oriented. There's now an open SHMEM movement, a little too late. There's global arrays, but global arrays is not just a communication framework. GA is compatible with MPI, and in fact it sits strictly on top of it, which is part of the project that I'm involved in. So this is really just about the lower level aspect of communication itself and distributed memory. We like to emphasize when people are proposing alternatives to MPI that, I said last week 99.6% of all parallel applications that of course use distributed memory are written using MPI, and somebody responded, that's it. So that should tell you basically, if you want to sort of be serious about parallel computing, not constrained just to a laptop or workstation or to a GPU, MPI is relevant. That doesn't mean that MPI is absolutely the best thing. Robert and I are probably going to make comments, particularly this afternoon, tomorrow, about things we don't like about MPI and things that are better than MPI. But sort of all of those things are in the limit. There's sort of the MPI is the CCSD parenthesis T of communication models. You could every once in a while you want more, but usually it's not worth it. Anyways, so distributed memory in contrast to shared memory. This is my awesome picture that I drew last night. I actually drew the struct version first because I was like, conveys the exact same meaning, but basically a distributed memory system, you have a bunch of nodes, and each node has cores and it has memory, and it might have local disk, maybe not. And then you build a machine up as, and there should be a pointer in there for machine to node, sorry, I forgot that part. But anyways, a distributed memory system is just a collection of shared memory systems. So they're not competitive with each other. It's just the distributed memory is the thing you do when sort of you run out of scope of shared memory. Now there's people who build very large shared memory systems, and they cost enormous amounts of money and don't generally deliver better performance for the scientific codes that we do. So anyway, distributed memory sort of goes back, so I guess I feel old all the time when I'm talking to students. Anyone in grad school is right now significantly younger than me, at least by computer epoch. So, but there's this whole thing about, you've heard of Beowulf and, their Revenge of the Killer Michael. So there was basically supercomputing was at some point a whole bunch of really exotic supercomputers, and then people figured out, if you heard about Moore's Law and Intel processors getting faster and faster and faster, you can basically just take a room full of computers, little computers, and bolt them together with cables and build a very powerful machine. But it was programmed a lot different relative to a big shared memory or big vector system. But that happened, and then PVM happened, and MPI happened, and sort of that basically became the future. And now all the supercomputers are actually modeled after that, rather than sort of the other way. So the differences are pretty striking in terms of programmability. So shared memory just allows you to do, you move data implicitly. If you say A equals B, data is going to move around all over the place in your hardware, and you're not really saying anything about it, at least not explicitly, unless you do assembly. There's, in distributed memory, somewhere you have to do communication explicitly. You have to say move data from here to there. Now, you may not see that because you may use some model that can make that disappear for you, but it's still there. And the reason is, shared memory, I don't know if this is absolutely the textbook definition, but shared memory implies you can do load store off of virtual addresses and get memory to move around, and you have hardware that when you say A equals B, the hardware knows to turn that into some set of operations in the computer. When you say A equals B and B is in a different process, in a different address space, the A, where you are, the process that owns your data, doesn't know anything about that. And your computers here don't know anything about each other. You can't just copy data off of somebody else's machine without establishing some sort of a notion of a connection to that machine. Now you SSH, you could build the shared memory or distributed memory on top of SSH and SCP. That's a way to move data, but it's very, very explicit because you have two different operating systems that need to know what language they're speaking when they're going to send data. Shared and distributed memory doesn't mean does not necessarily mean anything about performance. So you might say, oh, shared memory is always faster than distributed memory. Well, that may be true, but that's not at all in the definition. So I have a BlueJane system where distributed memory is, at least by one metric, faster than shared memory. That's a very odd concept, but there's actually plenty of cases where, in fact, because of the power of networks that we have, you can actually move data faster off the node than you can within them, and I'll hopefully hit on that. Now, in general, if you buy a computer that costs less than $25 million, shared memory will probably be faster than distributed memory, although you'll find, yeah.
Objection.
Which one?
Well, if you spend 25 million on a shared memory machine, it might be faster than a distributed memory one, but not the other way around.
Yeah, no, I guess I'm just contrasting cluster computing to BlueJane.
Right. Yeah.
If you pay for a very expensive network that's a very expensive distributed memory machine, the performance will be similar. But in general, yeah, if you build a supercomputing cluster out of the machines in this room and run them all over TCP/IP Ethernet through the router that's probably down the hall, you will find that shared memory load store within that box goes a heck of a lot faster, like 1,000,000 times faster, where it's like maybe a factor of 2 on a Cray, but that's part. Anyways, machine balance is a whole different issue. So there's something called distributed shared memory, and it's all I can say is basically it's ambidextrous. So if you buy an SGI machine, which is a very, very expensive shared memory machine, you have the benefit that if you feel like programming 100 or 1,000 cores with OpenMP, you can do it. But it's not a 1,000 core die that Intel fabs that's 4 feet wide. It's a whole bunch of Intel cores, sockets, strapped in boards, and those boards have very, very intelligent hardware that's actually able to turn a load store in that node into a network operation, and that takes work, and it's expensive, and that's why SGI machines are expensive. It's actually a very powerful thing if that's what you need, but it turns out you think about you're still going across a wire between two different motherboards. You go through a backplane, which is the thing that all the boards sit in. And by the time you do that, the performance is very different. So your load store over here and your load store over here, they're both load store, but they don't behave the same. And so it's a extremely NUMA. So it used to be that those were sort of called NUMA machines because all of our desktop machines were basically UMA. You had flat performance, but now we have multi-socket, multi-core, multi-cache, and so we have NUMA now in the node, and the difference in performance is much, much smaller than it is if you go from end to end on an SGI machine. So on an SGI machine, you can program MPI only, you can program threads only, and you can program hybrid. So you can do all the things in between. I would argue that based on the NUMA, you probably find MPI programs will run better on SGI than threaded programs, because most threaded programs are not designed to adapt to that level of NUMA. Now, if you get someone who writes an application for an SGI machine using threads, and they understand that it's this very, very large tree structure of, nodes connected in little boards and plugged into the backplane, and then you have racks, and understanding that there's this whole tree of hardware, then maybe threads will be competitive. So, but by the time you do all that refactoring, it's basically looking like MPI code only using threads. So, I know that was pretty heavy duty. I tried not to give too much of a hardware talk, but once we, in the same way that blocking for cache is, worth a huge amount of, performance on a CPU, you have to understand the memory hierarchy of a distributed memory system to program effectively. So we can go into this more later, but you should definitely run tests. I mean, you will find that MPI, load store generally behaves about the same. The performance profile of shared memory programs has a couple of tuning parameters depending on the hardware that vary over a smaller range than an MPI program. If you take an MPI program's performance and you go from 1 gigabit Ethernet running across a network of workstations in a department, which is the CS department at the University of Chicago builds a cluster out of everyone's desktop, which is really great for scavenging. You don't run a screensaver. Somebody's using your desktop overnight, but at the same time the performance is hideous. And you compare that to a Blue Gene, and you're talking about probably 3 or 4 or 5 orders of magnitude difference in an MPI program performance. So you have to think when you're designing a program how much effort you put into locality and minimizing communication depends on the balance of your machine. So if you're running Monte Carlo on a network of workstations, as long as you do communication, say, once every 10 seconds, you're probably going to scale out just fine. That will scale fine on any machine. If you're doing computational fluid dynamics or molecular dynamics and you're wanting to do an all-to-all on the entire system, all-to-all means everyone communicating with everyone else. It's sort of the ultimate traffic pattern or bad traffic pattern for a network. If you do that every tenth of a second, well, you're probably going to spend a billion times more clock cycles waiting for that to finish in a network of workstations versus Blue Gene. You can do an all V probably on the order of maybe a millisecond, and it's going to take many seconds if you're on a network of workstations, depending on if somebody's downloading at the time. Okay, so why does MPI exist? I have 2 books or 3 books with me, one of which is a book from 1994 on parallel computing, and it has a chapter in the end that's how to program distributed memory machines, and it goes through and talks about all the different APIs that people were using to program distributed memory machines in the 90s. And it turns out every single one of those APIs contains a function that has send and receive in the name, but they're all different, and they all have different particularities, and basically people realized 2 things. They realized, one, it was really annoying that every time you switch machines you have to go in and change your function calls. And then they realized the second thing, which is everybody was basically converging to, at least in regard to send receive, the same basic features. And so they got together and they unified those ideas into the MPI standard. MPI 1.0 was released. It was a very, very quick process relative to standards bodies. I guess Robert, you were there for a good portion of that, and then MPI has sort of grown enormously since then. It was originally sort of a thin thing to, as best I can tell, unify send-receive models and provide some other important features. And now it is sort of the all-encompassing API for parallel computing. It has over 500 functions, 90% of which you will never use, but they exist for a reason. So application programmers, I will argue, have benefited an enormous amount from the portability that MPI offers, and they benefit from the portable performance, but people are technically giving something up, because when you have a portable program, it's like the difference between assembly language, which is not portable, and C or Fortran, which is portable. Some of the time it doesn't matter at all, but in as Robert showed, there's some examples where you really dial down to a very, very small function call or something, and you possibly see a difference. So MPI assumes, so least common denominator is a mathematical nonsense term. It's not. There's no such thing as a least common denominator in math. Bill Groff is often point this out. Bill Groff is sort of like the Linus Torvalds of MPI in some regards, except he doesn't swear at people. He's very, very nice. But least common denominator is sort of just, MPI doesn't provide things that don't work on some machines. So if there's a really exotic, amazing feature of one supercomputer, MPI is not going to go running after it. Now, if all of a sudden they discover that 80% of the machines support something well, and the other 20% can do it if they have to, that sort of becomes eligible for support in MPI. One-sided communication, which is something I'll talk about tomorrow, is one of those things. And one-sided communication is really terrible on gigabit Ethernet, but it runs really well on InfiniBand, like Hokey and high-end systems. And so MPI provides it, and it is functional on really cheap networks, but not at all very performant. But then it starts to change in its performance characteristics as you pour dollars into the machine. And then if you read the MPI standard, which I do almost every day because I'm a weirdo, if you read it, what MPI is assuming in there doesn't necessarily match up with an implementation. So MPI is a standard, just like there's a Fortran standard, an OpenMP standard, and whether or not a compiler or a runtime or an MPI implementation do everything exactly as you'd expect in the standard is an open question. So, but usually they do, and there are some very good implementations. And the other thing, MPI standardizes a best practice. It's not a vehicle for research. So they're by definition behind the times. MPI waits until somebody proves that you can do something, you can do it effectively, you can do it portably, and then they will standardize it in a way that is very thoroughly discussed. We worked on MPIs. I attended my first MPI forum, and we voted on 2.2 at the very end of grad school, and we ratified MPI 3 last year. So about 3 years for MPI 3, and that was a fairly vigorous effort continuously. So from the ideas that went in 2010, it took sort of 2 years in the hopper, people trying to hash out what the details were before that actually goes into the spec. And it only, if you exclude MPitch, which is the reference implementation that runs on laptops and workstations, it won't be until, I guess, NERSC just installed MPI 3 from Cray on Edison like a couple weeks ago. So that's the first deployment of MPI 3 on a high-end system. On Hokey Speed, you can get it from MPitch. As far as I know, I haven't done much evaluation. So there's a lag there of 2 to 3 years for stuff to actually be available. The other thing, do not be intimidated by the MPI standard just because it is massive and has things that make no sense to you as a scientist, like what is a communicator attribute, what is an error handler, why do you care? Well, the fact is you almost certainly don't, because you're an application developer. I would say about 90% of the function calls MPI exist for people to write other software, for people to write libraries. So when we write libraries like to do ARMC and to do global arrays, we use things in MPI that you guys probably will never touch, because it's a way to get composability and to ensure that when you run your different libraries together, that they all play nice and you can store information in a portable, extensible way. But they're not really functional for computational science. Okay. So sadly, it's broken like the last couple days for reasons that I don't know. So if you want the latest spec, I just send you a PDF, but you probably don't because it's about 800 pages. This is my copy of the MPI standard. It is 800 and it's over 800 pages long. I have read it end to end, but I don't think very many other people have. So MPI 1, which was a lot thinner, probably about 200 pages or something, was all about message passing. Message passing is what it sounds like. I pass a message to someone and they receive that message. Or we can do a collective message passing where I can pass data to all of you or vice versa. MPI 2 and beyond do other things. They don't just do message passing, but they decided not to change it to the parallel programming interface or something else like that. It's still called MPI. There's a big disconnect. You will hear people talk about MPI, and they'll be, what they mean by MPI is, when they say it is send, receive, or collectives, not what is actually in MPI. They sort of carve out a little subset. You know, it's like saying that MP2 is quantum chemistry, okay? It's in but not equivalent, okay? And this is important because there's a whole bunch of other things that MPI does and actually can do well that people just ignore, or people don't understand. Then the other half of it, not just the standards, is the implementations. So I was saying this a few people walked in this morning. So there's a couple of open implementations. MPitch and OpenMPI are both open. OpenMPI, the fact that it says open in it is, I mean, it's just part of their name. Also, just small pet peeve, understand the difference between OpenMP and OpenMPI. It's a great way to make yourself look dumb on Stack Overflow is to say, I'm writing an OpenMPI program with 14 threads, and or saying, I am using the OpenMP, you know, for message passing. People just assume that you have been around for about 12 days in programming and are less inclined to help you, or they will treat you like you are extremely ignorant. So anyways, they're both good. I use both of them. Like I said this, earlier, MPitch is developed at Argonne by my close personal friends. I'm extremely biased, but I do use OpenMPI when I want to motivate my close personal friends to make feature improvements to MPitch. So all I just basically say, blankety blank isn't working. If you don't fix this tomorrow, I will use OpenMPI. Yeah, I'm not serious, but anyways. OpenMPI and MPitch now have very, very good desktop support. MPitch has a terrible reputation on sort of workstation desktops because of something called MPD. MPD is terrible. The guy who wrote it as a hack to get them through a period of time when they needed something quick and dirty, and sadly it was sufficient, and therefore people just kept using it until like 10 or 15 years later people were like, God, this thing really sucks. And it was like, yes, of course, it has always sucked, but somebody has to step up and write a better, you know, process logic. So there's now something called Hydra, and you use MPI exec, and on clusters and on your laptop, the magic happens. So if you get an error message that says it involves if you ever see a warning message that contains this string from MPitch, delete that version of MPitch and get one that was made in this century, okay? And if you ask a question about this on the MPitch, they send this message pretty much all the time. They have an FAQ thing called, I don't like, insert something here about MPD, and the response is, yeah, we know it sucks, stop using it. This is how you install the alternative. Okay, so MPD is totally dead, but it's part of the reason people don't like MPitch. Anyways, so I'm not saying you have to like MPI. You might actually like it. You might find it's more than sufficient, but you do have to understand it if you want to program, you know, more than one computer. There's pretty much, the alternative would be to learn TCP/IP, and if you've ever looked at that, you will come running back to MPI. Okay, so Hello World program. So the first thing you see here, so there's a lot more characters than for the OpenMP equivalent, which if you don't remember, it's in the repo. But everything is a function call. Whereas OpenMP is predominantly pragmas with a few runtime calls. MPI everything is a function. There is no language or compiler support. MPI has bindings, meaning sort of an interface for C, and for Fortran, it has 3 different Fortran interfaces. We can talk about that later. If you're a Fortran programmer, you are almost certainly better off writing in C, the MPI stuff in C, and writing your own wrappers into Fortran for reasons that I can talk about more later. There were C++ interface functions. I didn't exactly lay down in front of the tank, but they almost, they sort of deleted them against my extreme protest. The reason that they were deleted is they had no value added over the C ones, in the sense that, or no significant value added, that they basically all looked the same, but they had C++ essence to them. And people's argument is, these are hard to maintain and you can just translate one-to-one to C. So if you're a serious C++ programmer, there are motifs that you use in C++ that really don't have any, they weren't represented in MPI and their MPI standard, so you weren't getting sort of any of the benefits. So I am currently sort of doing a little bit of survey on what people actually want out of C++ MPI binding in hopes of not necessarily standardizing anything, but trying to come up with something that's sort of better that makes C++ people happy. So if you're a C++ person, use the C bindings. If you're a Fortran person, use the C bindings. C bindings are good. And there's actual, like, genuine technical reasons why you want to use the C bindings. Fortran has some really awful dark corners that nobody really understands that allow compilers to do terrible things that can break MPI programs, and there's almost nothing you can do about it other than assume that your Fortran compiler doesn't do terrible things. So, what does this program look like? This will be my pointer. So, this is just, the arguments. I'll talk about this in a second. So this is MPI init, MPI init thread. I'm only going to use MPI init thread because you should be writing threaded code with MPI, and if you do that, you need to use init thread. This is the beginning. Before this, you can assume nothing. I mean, it's sort of like, the Big Bang, or, the first, 12 sentences of Genesis, before MPI init, there was nothing, and then MPI init made everything. The thing is, it's very important, you can't assume anything before MPI init. How many processes are running? Is it one? Does MPI init fork and fan out a bunch of processes like OpenMP does? Or do all the processes start and MPI init just rendezvous them together and says, now we're going as a team? You don't know. And there are technical implementations of both. The one where you have no parallelism before MPI init is not common anymore. That's more sort of for exotic supercomputers that are strange. Almost everything today, if you were to print, print a message before init, you will get n messages, and you will get n messages after. But the other thing you can't do is you can't touch argv, argc, technically. I mean, you can, and you can determine that on some platform it's okay. But one of the reasons is that depending on how your OS handles argc, argv, there are arguments that you pass in addition to the program argument, such that if you say, oh, the first argument is my input file name, well, and you say, oh, that's input.nw is argv1, right? You want to look for that. Well, if you do that, and your OS doesn't sort of parse the fact that you're getting MPI stuff before, then what you will actually get for argv1 is like -n, because that's the first argument to MPI exec, the thing that launches NWChem, for example. Just basically to do main or a program or whatever you say, and then say MPI init immediately, and then your life will be fun. Then standard things, who am I and how many of me are there? Just like we have get num threads and get thread num, there's size and rank. So size is how many processes are running, and rank is who am I in there. So rank 0 is sort of your master, but all processes in MPI are equivalent for the most, with one caveat that you never ever are going to have to see. So unlike threads where there's sort of a well-defined master, I'll talk about com world in a second. So, and then you have finalize. So finalize says, okay, we're all done, close everything down. And this matters. You can, if you want, you can just call exit. It's not really a correct program. It will work. if you were to do that on certain systems with an MPI implementation that did certain funny things, even on like an InfiniBand system, you'll find that bad things will happen and the sysadmins will come and hunt you down. MPI is better now, but at least there are other communication libraries that actually will leave all sorts of system resources open and dangling, and then you do that over and over, and then you all of a sudden realize you have none of those system resources left because they're all being consumed by processes that no longer exist. And then after finalize, similarly, assume nothing. You have no idea whether or not finalize behaves like a join or not. So if you had 50 processes here, you could have 50, you could have 1, you could have 37. It doesn't really matter. More than likely you'll get 50, but don't assume that. Okay, so unlike threads where you just have one scope in OpenMP, you basically have here are your threads in this process. So you have this thing called MPI COM world. So this means this is the collection of everybody. So when you call MPI exec, you launch on 50 processes. COM world contains those 50 processes. If you write an application code, a simple application, you can use COM world. If you write a complex application or a library, you don't want to use COM world because you want to do something called dupe-it, which we'll talk later. The reason is that a communicator is and this is actually, you know, Mark Schneer is one at Argonne now is one of the I don't know, top 10 like all-time fathers of MPI figures, you know, said that communicators are sort of like the one huge lasting intellectual advancement that went into MPI. A lot of MPI is just recognizing and standardizing best practice, but communicators are actually sort of really novel. They're sort of like, I don't know, I'm not a ham radio person, but I mean, you guys understand radio stations, right? So if you tune the dial to a particular radio band, you know, or it makes more sense if like you're on the road in semi-trucks, right? You're on band 14, right? And all the trucks that are on band 14 can talk to each other. But if you're on band 50, you don't hear anything from band 14, and you can't talk to band 14, right? So there's a nice separation. It's like it's a frequency channel. Channel has a number of meanings in communication, so it's the wrong term exactly, but maybe channel in the radio communication sense makes a lot of sense. So it's sort of a plane in which communication occurs, and it is good to separate out planes because then you know that you don't get crosstalk. So imagine that I want to read in my input file and broadcast my basis set to all the processes, and at the same time I'm initializing a library which is going to, you know, read in a matrix and broadcast that matrix to everyone. So how do I know that, you know, how do I know that those two things actually don't conflict? How do I make sure they're properly ordered? Now I can make them fully sequential, but maybe I want to communicate point-wise, and maybe I want to say I'm going to move my particles here, and I have, you know, a background charge field, you know, I'm thinking like sort of some couple particle mesh type simulation, and you want to sort of keep your particles talking to each other and your mesh talking to each other at the same time. How do you make sure that those things actually line up? Well, you stick them on different communicators. So you could have MPI-COM mesh and MPI-COM particles, or you could have MPI-COM density matrix, MPI-COM Fock matrix. These things are not always necessary, but that's really essential. And so you can turn one communicator into others, so you can split them, you can combine them, and so that's why we need to know which rank and size. So you can in fact you know, split it in half and say I'm going to run, you know, something over here and something over there, and then you will have size being the original size divided by 2, and then you'll have rank 0 through n over 2 and 0 through n over 2. Okay. I know this stuff is really dry. I don't really know a good way to make it snazzy. Learning MPI is sort of tedious at the start, and then hopefully it gets easy once you start writing code. So I said some of these things already. So funny thing, we say MPI processes. We do not necessarily mean OS processes. There are MPI implementations in which processes are actually threads. The The reason I tell you this is that if you have global variables, technically that's wrong. You won't actually notice it because unless you buy an SGI machine, I don't think it's relevant. But technically they're not guaranteed to be OS processes. The scope, so world is the default scope of everyone. The other one is self. You can imagine who is in self. That's your local process. It's not really that useful, but it is sort of a construct from which you can derive other things. And you can also sort of determine, you could say, you can determine that you have one process by just saying size, determining size is one, or you could just say is world and self the same, and then there's some other aspects of this. Okay, so a lot of people think of MPI as being all about send receive, but I find that send receive is not really the primitive that I like to use, and so I'll talk about collectives. So collectives are collective operations, so they involve everyone on a communicator. They don't necessarily involve everyone, but they do. But if you have a communicator with this global scope, it will involve everyone. So there are a handful of these. So barrier moves no data. It is a barrier. It is a process synchronization. So if you want to say, okay, iteration 0 starts, call barrier, do iteration 0, and call barrier. Now you know how much time it takes to implement it. That is an unnecessary use of barrier. You will almost inevitably do it yourself, and everyone else will do it. The only reason you should actually use a barrier is because you need to know that you've synchronized all processes for some reason. But we talk about race conditions and memory models and things like that already. If you don't actually move data, why do you need to synchronize? So it turns out that really the barrier is just a very heavy hammer for if you know you need to synchronize a whole lot and it's easier to just call a barrier. Because barrier tends to take essentially no time. Like on Blue Gene, you can barrier 800,000 cores in less than 10 microseconds or something like that. So that's, try to do 10 microseconds on a stopwatch, and we're talking about 800,000 cores. So if you do anything else, it takes a little bit longer. So there's broadcast. Broadcast is me right now. I'm broadcasting this very dry content to all of you. You're all getting the exact same thing. Scatter is if I, pulled out, a bag of rocks and gave each one of you a rock, I would be sort of scattering my pile of rocks. You'd all get your own rock. If I then said, okay, I need all of my rocks back, that would be a gather. I would go and get each of your personal rocks, and I would get them back, and then I'd have, so you would give me one rock, and then I would have n rocks from all of you. So that's 1 to n to 1. There's all gather, doesn't really work with rocks, but if I had a magical cloning machine and I was to gather here's a good example. So birthdays, it's funny because now that I work for the government, I'm always thinking about PII, so I can't actually collect your birthday. But if I was to ask you for all of your birthdays and then write them all on a list and then give you all the whole list so we could all decide whose birthday we're celebrating next, first of all, I'd violate all the PII rules that I'm supposed to abide by. But that's an all gathering. So I'm gathering all of the information and then I'm broadcasting. Now, that doesn't mean that all gather is implemented as somebody does a gather and then immediately does a broadcast, but that is the equivalence. So many implementations of MPI functions are much, much faster than their sort of equivalent in terms of simpler constructs. Now, all is all gather only where you have different output. All is sort of the, it's end to end. The best sort of, think about fast Fourier transform or a matrix transpose. If you're doing a matrix transpose with, column major with distributed stuff, you want to do transpose. So you're going to take, I own all of vector 1, right? So in the transpose, if the data distribution is the same, all of you need to get a piece of vector 1, and that is true for all of us who own vectors, have to sort of split up our vector and give it to everyone else. So everyone is taking some data set, chopping it up and giving, so all is equivalent to all scatter. So the analogy from gather to all gather is scatter to all scatter, except I guess all is easier to think about. Reduce and all reduce are combining operations. So if I said that, I need to buy an amazing, collectible, Beanie Baby on eBay, and I need all of your money, I can do a reduce, right? I can take how much money do you have, and I can do it all reduced with sum, and I can sum up all our money and say, oh cool, we're gonna spend 24 grand on Beanie Baby. That's a totally 90s analogy, but I couldn't think of anything better. And all reduce would be you would share. Now, so all reduce and reduce are really, really, really common in numerical computation. So you're running your Hartree-Fock solver. How do you know that? What's the energy? So everybody has a contribution to the energy. If you want to know that energy at one process so that that process can write it to an output file, you do a reduce. If everyone is going to say, if the energy is less than, if the energy convergence, energy difference is less than 10 to the minus 5, and everyone needs to know that, then you do an all reduce. So everybody knows that the residual is 10 to the minus 5. So, reduce and all reduce, at least if you want to write simple parallel programs, you may find that these are two of the things that you're going to use a whole lot to start. And you can actually write an amazing number of parallel programs, some in fact quite complicated, using just these constructs. There's also something called reduce scatter. It is exactly what it sounds like, reduce plus scatter. It can be implemented better, it often isn't. Reduce scatter is really useful in linear algebra, so you can imagine reducing all of the vectors and then doing a scatter that shows up in lots of matrix computations. There is a thing called, and then there's vector arguments. So you'll find that there's a gather and a gather V. So gather is the scalar argument says, I'm going to gather one floating point number from all of you. Gather V says, I'm going to get one floating point number from you, and 13 from you, and 8 from you. So I have to provide a vector of how many numbers I'm going to get from everyone, okay? So turns out that these V-ops, you want to avoid them if you're on, say, 1 billion MPI processes, which most of you don't have, but I do. So why might you want to avoid having a function that takes a vector that's 1 million elements long? How many, if you have 1 million integers, how many bytes is it? 4 megabytes? Well, long integers, yeah. So MPI always uses 32-bit integers. So it's 4 megabytes. So the CPU has to go in and read a vector 4 megabytes long, which thankfully now doesn't blow out cache completely, but that's a lot of data to read through. It turns out that you can find an all-to-all V on 100,000 cores or something that, if you have Blue Gene P or something, you can actually spend a decent amount of time reading the argument. There's something called all-to-all W. It's sort of the ultimate generalized collective. I think you can write essentially everything as you can write basically everything as all W. Please don't ever use it, it's terrible. It is nice in that it's like that Swiss Army knife with 50 things in it, and it's got a toothbrush and I don't know, a screwdriver for a screw that only existed in Arkansas in 1965 is got something for plucking your eyebrows. I mean, who knows? It's got all these tools, and it's just yes, of course, it'd be fantastic to have a pocket knife that weighs 5 pounds and has every tool, but that's not actually what you want. So don't use all W. It is a really terrible function, and it doesn't scale. And there's only one reasonable use case for it, and even then, no one uses it for that. Okay, so broadcast and reduce. So this is sort of, I think of this as if you want to write a fork join style program. It's not a fork join because, like I said, init and finalize may or may not be forking and joining processes, but in terms of process control, if you want to start with info at a master and give it to everyone, and then everybody does something like Monte Carlo, the canonical example that I've written and that you'll see, it's the program that you run, first thing you run after you install MPI to make sure your MPI is working, is CPI. And CPI is compute pi using Monte Carlo integration written in C. If that program doesn't run, something is wrong with the MPI implementation. And basically what it does is it calls broadcast. It'll say, I would like you to do 1 million Monte Carlo samples, and then it reduces and says, I sum up all the statistics from my Monte Carlo that it ran independently, because of course Monte Carlo is ridiculous parallel, and then you sum up and you get pi equals 3.14126, or something that's a little bit off because you only ran it for 1 second. And that program's in the repo. In my version, you can run it. Let's look at a little bit of this. So broadcast takes one sort of data argument. It's an in-out. It's in at the root. So I'm broadcasting. It's an input argument for all this content, and for you it is an output, as in it's a receive. You're receiving data into this buffer. Count is how many elements, how many data elements of a particular type. MPI int is the type. So this says I'm going to pass count integers, C integers, in this buffer in out. Root is the person who is actually doing the broadcast. Anyone can be root. You can broadcast from 0, or you can broadcast from n/2. And then ComWorld says this collective will happen on the ComWorld channel. Everyone has to participate. Now, if you put like if rank not equals to 47, and then you call broadcast on ComWorld, that program will run forever. It will deadlock because broadcast is collective. Everybody has to participate on ComWorld, and if you say if not 37, you have 47 is not going to participate. Interestingly enough, if you were to intentionally write that program, you'd be in violation of Virginia Tech's computer use policy. I read this. I actually read those things every once in a while. It says you're not allowed to intentionally put a computer into an infinite loop and use up CPU resources. So obviously writing bad MPI programs is not, I'm sure that they would be okay, they wouldn't come after you for writing bad MPI programs, but if you're like, ha ha ha, I'm going to deadlock my MPI program infinitely, you are, Virginia Tech says you're a bad user. So be ready with Control-C, because I actually have a program that will deadlock for educational purposes, which you should kill, and I'll run into. So then there's the reduce at the end. So reduce has 2 arguments. Everyone provides an input. Everyone's going to contribute something to the reduction, and then somebody, the root, is going to get it out. If it's an all reduced, everyone gets the output, and there is no root argument. Sum is the operator. So sum says we do, y plus equals to x for all at all processes. There's sum, min, max, prod, max, loc. These are all documented, but sum, min, and max are probably the most common ones. Max is like find the most likely drug target. Min is you want to minimize the or max L1 norm. Min might be who has made the least progress on my thermodynamic sampling. Some might be what is the residual of my couple cluster iterations. So these are the ones that are sort of commonly used. And so, yes. All right, so those are all collectives. They're extremely powerful. You write bulk synchronous programs where everyone computes, everyone communicates, everyone computes. Sometimes that works. Sometimes it doesn't. There's not required in all programs that everyone has to be involved in communication all the time. So there's send and receive. So send and receive have long historical precedence, long before MPI. There's send receive in almost any communication layer in TCP, and so the thing is they're two-sided. And they're almost symmetric. So one way I try to think about this is send receive is sort of like a telephone call, right? So I call somebody on the phone and it's going to go ring, 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 and I'm going to sit there, and then they're going to pick up, and I'm going to say, hey, guess what? Your dog ran into my backyard. Do you want your dog back? And the person's going to say, oh yeah, sure, thanks. And then I say, oh, your dog pooped in my yard, so you have to come pick him up and poop in my yard. And sometimes happens. But so there's a two-sided aspect to that. Text messaging is one-sided. So I just text you and say, your dog's in my yard, come pick it up now. And at some point you'll turn on your phone and that message will be there. But send, receive, in this case, these are blocking. So this means I'm going to sit there on the phone until you pick up. So you guys probably haven't lived in a world without, call waiting and voicemail, but there were days when like the phone would technically ring forever, and that's what send and receive will do. So let's see. So you have an input and buffer. So these are buffers in the sender and receiver's processes. So this void buff is not the same, unless of course you're running in one process. Count, same thing. Data type, same thing. Source and destination. So send, I call send is who am I calling, and then on receive, source is who's calling me. So when your phone rings, you look at caller ID now, but it's not like you can only pick up the phone if a specific person is calling you. There's actually an argument for source called any source, which says I'm going to pick up the phone. I don't care who's calling because they're calling me. So there is no such thing as any destination because that makes no sense. You can't pick up the phone and call an undefined number, but you can pick up the phone and accept the phone call from anyone. So that's a small asymmetry. Send, receive happen on a communicator, so there's a channel. So it's a bad thing if you get phone calls that are aimed at your neighbor or from another country. Not if three countries have a phone number, 147258, you'd like to make sure that calling those numbers in those countries goes to that number in that country and not to that number in some other country. So communicator is sort of like a country in the phone sense. Status is, why does status exist? You say, oh, well, I've got my buffer, I got my count, I got my data, I've got all the information I need. What could I possibly need out of status? Well, this should tell you that there's something not entirely complete about these functions, which is, and this is a historical artifact, I think. It is useful, but it is quirky, which is there is no requirement that send and receive give the exact same amount of data. You get phone calls from telemarketers, and they want to tell you a lot more than you want to listen to, right? Hopefully that doesn't happen anymore. I don't pick up the phone in for that reason. But so what this means is you can send 1,000 bytes, and somebody can receive 500 bytes. I don't personally find that to be useful, but it is the generalization. The reason status exists is so you can query that. So I say I'm going to send you 1,000 bytes, and you post a receive for 500 bytes. And you don't know. You can cast things to different types, and so you can get information out from the status. The other example is, let's say I'm waiting for 1 megabyte, and you only send me 15 kilobytes. I actually probably need to know that you didn't send me all the data I was expecting in order to write a correct program, and status would allow you to say, oh, it turns out you didn't send me the full message. So the other thing, these buffers, because they're addresses in the respective processes, you have to have a match, right? So if I do a send, I can send from some buffer. There's no way for me to know what address that data needs to get written to in your process unless you post, receive, and actually send. MPI doesn't have psychic powers. It needs to be told which buffer on both ends to put data in. Now, there are other ways around this. One-sided communication changes this and separates out the sort of matching concept, but that's an important element that there is a two-sided nature because we have to agree that I'm going to send you data from somewhere and you're going to receive data into a specific place. So there's a lot of books on MPI. Using MPI and using MPI2 are quite good. They cover, they go depth first into there's like 7 versions of send, receive. There's all sorts of different stuff. I'm not going to try and belabor and enumerate all the different things you can do. I'm going to talk about this because it's a concept that's not, it's in the MPI standard, but it's not in books, and I think it helps. And since you're all smart enough to believe in or understand quantum mechanics, or at least believe that it works, you can probably handle message envelopes. So a message envelope is source, destination, tag, and communicate. Okay, so that's sort think about radio communication. So you have to be on the right channel, and at least in the send receive sense, you have to have source and destination. So you can say, oh, you know the difference between the U.S. telecom network and the Brazilian telecom network. So you've got that worked out, and you know that you're dialing 140358, and somebody else is going to pick up. And then there's a tag, and so the tag is a way to sort of granularize. So let's say I've got a communicator, which is I'm going to exchange particles in a molecular dynamics simulation, but I'm going to do it in 2 phases. So I'm actually going to exchange all of the water molecules first, and then I'm going to exchange all of the sodium chloride ions second for whatever reason. Okay, so maybe I actually want to have the same communicator, but I want to have tag water and tag sodium, tag chloride. So that means I can do a receive on water and know that I will only get messages that contain data about water molecules and not, so I won't accidentally insert coordinates of water molecules into the structure that holds the coordinates of sodium. So in a message envelope, you have to match, and you can match with wildcards like any tag and any source. But if you don't match, you're just sitting on the phone, and the phone is ringing forever, and your program deadlocked. So it's important to understand that these envelopes have to line up. So like I said, so you can pick up the phone when anyone's calling. There's no such thing as any destination. It just makes no sense. I've gone through some of this and that and that. So the important thing is that count and data type are not in the message envelope. You do not have to match those. There's a misunderstanding that you can match like between int and double. That's wrong. You can match between byte and anything, and a weirdo data type that you don't have to worry about in anything. So you could say do a send of doubles and a receive of bytes, and as far as I know, that's valid. But you can't do send of doubles and receive as ints, even though it probably doesn't matter, and MPI would probably do it for it. It's not correct. And if it's possible that the count doesn't match, you need to query to make sure how much data you actually got. So what does this look like? This is actually an excerpt from a program I have that doesn't fit on a slide, but it's interesting, I think. I'll talk about it on Wednesday. So I do a receive. I'm receiving this info object, which is a struct. So I receive this many bytes, and then I'm actually polling. This is a server. It's actually an implementation of one-sided sort of active message communication. So I have a thread that just spins in a loop that says, if somebody sends me, if anyone sends me message info, I'll receive it from anyone. I'll only receive, on this thread, I'll only receive info tags. So I'm only going to receive stuff that's actually a message info struct and not any other data, because it might be that there's other things that are the same size in byte streams that I don't want to receive, and then I have message com world, so I have my library as its own communicator, so that if I do this receive, I won't match. Because if I have any source, an info tag, there's only so many tags, I can accidentally receive the wrong data. And then afterwards I can say, who sent it to me? Because I might actually want to know that. And I say, what was the tag? Well, in this case, it doesn't matter because I specified the tag, but if I put any tag here, I look at that. And then I can say get count. I can say how much data was actually there. In this case, I'm only doing it as a sanity check. There's no way that my struct changes size because I'm on a homogeneous platform and the C struct should change byte count, but I can do that. Now, so send and receive are blocking. The phone will ring forever and you'll just sit there. There's a concept, I don't know, have you ever called like your credit card company and they're like, the wait time is currently 3 hours and 14 minutes. Press 5 and we'll call you back when someone is ready to talk to you. I mean, it's rare, but that's actually happened, right? So some nice corporations will do that, okay? So this is sort of like non-blocking, right? You basically say, I would like to send 1 megabyte, and you just say, I'm going to send 1 megabyte, but then I'm going to hang up the phone and assume that the phone is just going to magically take care of it, and the phone will ring when it's done. Okay, this is a loose approximation. This is sort of, these are in queuing operations. So send and receive with an I in front, they return immediately. That doesn't mean they return instantly. They return immediately, meaning as soon as they are done initiating the operation for some definition of initiating, and they don't wait on it to complete. That's really, you could also, a better way to think of the I for educational purposes would be to think of I meaning incomplete. This is an incomplete send receive, and at some point later, you need to actually complete the operation. The way you do that, you get a request back. The request is just an opaque object, except in Fortran where it's an integer, one of the many reasons that Fortran, old Fortran is bad. But a request object is the thing that allows you to say when you're done, okay? I can think of good analogies, but I think it's a fairly transparent concept. Now, incomplete send receives, non-blocking send receives. The buffers are read-only. This is sort of they fixed this in MPI 2.2 because users weren't obeying the rules and they were reading their buffers while they were in flight, which is totally valid, except in weirdo implementations. So buffers are now, it's okay to read them. You cannot write to the buffer, and you cannot free the buffer. So if you do an ISend and then call free, God only knows what happens. Either MPI is going to scream bloody murder, or your operating system is going to scream bloody murder, or you're going to see a glibc, what the hell is free, corrupt, whatever. Terrible, terrible things will happen. So please leave your buffers. Don't touch them. If you forgot what's in them, you can read through. You can do a send, and then you can read back the data for some reason. I don't know why. But don't modify, free, or otherwise perturb the data while the message is in flight. Same thing for an iReceive. If you post an iReceive, you can't do anything with that buffer. Okay, the data has not arrived yet, and even if it has, it's like Schrodinger's cat. Okay, if you go look in the buffer, who knows what's there. It could be there, it could be not. It won't kill MPI to do that. You just will get a nonsensical program. You have to complete these messages before you can actually query. Unlike send receive, where if you do a send and the function call returns, that means you're good to go. You can do whatever you want with the buffer. If the receive returns, that means the data is there. So the way you complete your non-blocking or incomplete send receives is you can wait, okay? So you can wait on them, which is you will just block until that operation completes. Or you can do test. Test is pretty much exactly what it sounds like. You could also humorously think of it as a non-blocking wait. We occasionally, we're huge dorks in the MPI forum, and we think about things like, MPI iWait, returning its own request object, and anyways, it's just total silliness. We post some funny stuff. There's some great tickets from April Fool's Day about things like this. So there's any, some, and all version of this. So there's like test any, wait any, test some, wait some, test all, wait all. And that's just ways of obviously getting, multiple completion events, and any, some, all determined. Any will basically say the moment one and only one of these things is done, return. So if you do wait any, you will wait for any one of the operations in the array to complete, and then you'll come back. If you say some, it can sort of complete more than one of them, but not necessarily all of them. And if you say wait all, you will, of course, wait for all of them to finish. So there's good uses for these. I think, polling loop, like in Madness, I think uses a test any or something along those lines. It is advantageous, both for performance and correctness, to fire off your non-blocking stuff and do a wait all or a wait, okay? I found, when I learned MPI, I was also learning C at the same time, which is really, I didn't understand pass by value, and my life was really awful. And one of the things that among other things that I was tortured by at the time is the blocking send receive have the potential to deadlock. Because if you don't match them right, they're blocking. It's like, and this again, this is probably not in your lifetime that you've actually picked up a phone and this has happened. But like if you were calling somebody and they were calling you, in some temporal ordering of the things, you could both be like, ringing indefinitely, waiting for the other person to pick up while you're both on the phone. And obviously, somebody has to hang up the phone for this to work. So the other thing is it's really advantageous for performance on what I will argue are well-behaved systems. So on Blue Gene, if you do a lot of non-blocking and then await all the performance is awesome. On some Cray machines, it can actually be an issue. It shouldn't be the implementation, should be able to work around it. It has to do with the relative balance between memory bandwidth and network and things like that. But I'll show you on Blue Gene in a second how performance is advantageous. So I wrote this program last night and confirmed that it is in violation of Virginia Tech's no infinite loops policy. Obviously, if you define deadlock, so here's what happens. You do a send, and then you do a receive. So imagine this thing will deadlock on any number of processes. It will deadlock particularly well in only one process, and this is I'm going to send to myself, and then once I receive my own message, I'll return from that send and receive that message. You can imagine this doesn't sound very intelligible. It doesn't work. If you do this from threads, it will actually work because one thread can send and the other thread can receive, and that works. Probably don't want to do that, but you can. The other way to do it is to say I send and I receive. So I'm going to say I'm going to enqueue a send, and then I'm going to enqueue a receive, and then I'm going to wait on both of them to finish at the same time. And MPI is smart enough to say, oh, good, these two things are going to cross, in midair, and then they're both going to arrive, and then I'm going to know both of them arrived, and then I'm going to return. So this program works just fine for any number of processes. This one doesn't. One of the exercises is there are some cases where this doesn't deadlock. And you should try to figure it out, and then I'll explain why. It has to do with the bowels of how MPI actually works, where this is okay. So what that means is just because your program works some of the time does not mean that it's a correct program. Okay. Just like anything, the absence of errors does not indicate the absence of bugs. It's just that the presence of errors probably indicates the presence of bugs. These are matched, and obviously if you don't match, things get screwed up. There's also this, I'm sort of doing this a little bit evil. I mean, it doesn't really matter, but usually you want to pre-post your receives. Normally you want your receives to go first and then your sends. The reason is, when you post a receive, blocking or otherwise, you sort of prep MPI to, it's like turning your porch light on when you know somebody's going to come over late at night. It's just a nice thing to do. It makes sure that when they come up, they don't, trip on your front porch and break their leg and sue you. If instead you turn off the front porch light, or turn on the front porch light after you hear some wailing and gnashing of teeth on your front porch, obviously things don't work. So pre-posted receives are generally a good idea. Here doesn't particularly matter. This is all implementation details. You can find all sorts of crazy quirks on all sorts of different machines where things are or are not intelligible. This is in general, this is harder to deadlock. I mean, I think there's a way to deadlock this. If you don't use wait all, you can obviously have non-matching sends where they just don't complete because you don't have. If I put tag 1 here, for example, and tag 0 here, this will deadlock because it'll basically wait for a message of the wrong tag forever, and there never will be a message arriving in this program. It's educational. You guys should use either the Kernighan debugger, meaning printf statements and thinking, or you can use GDB, which is a real debugger, and figure out where that thing deadlocks and what it's doing when it deadlocks. That's a good exercise. And then figure out when it doesn't deadlock. So there's an argument to this program. This is not the full program, obviously. The first argument is the number of bytes that you're going to send. So that's hint is the number of bytes affects, in some cases, whether or not this thing deadlocks. It also depends on the number of processes. basically there's one process, and more than one process is one option, and big and small messages are the other two options. So that's a 2x2 search space. Everybody should figure out the answer. And I haven't sort of belabored the details on how you launch an MPI program. You can launch an MPI program as a serial program, just like you would a serial program. MPI should work if you do that. It doesn't work on a Blue Gene, but Blue Gene is special, but on a Linux system it'll be just fine. MPI exec is, so there's MPI run, which is sort of the older launcher, and MPI exec is the new one. There's a whole bunch of reasons to use MPI exec. I don't happen to know all of them, but I just don't. You'll read MPI run everywhere, but just every place you see MPI run, replace it with MPI exec, and there's arguments like NP and N that you have to switch, that the man page is perfect, or MPI exec dash help, obviously will tell you stuff. So you say N is the number of processes. If you have dash N, like environment variable, you can pass environment variables. MPI exec does not necessarily export your shell environment to all processes. It will on your laptop, but if you're running on hokey speed, you call MPI exec, you're calling MPI exec on one node, and the program may launch on 50 nodes. There's no reason why MPI is going to go clone the operating system image so that your whole shell environment is over there. So and you wouldn't want to anyways. So if you need to say, so you program maybe say get in verbose printing, right? And then you might have that, so you need to broadcast that environment variable. And then this is of course the standard variable. This is actually not standard. It's pseudo-standard in that MPI exec and MPI run are supported by all the common sort of portable implementations of MPI. But if you're on a Cray, you use AP run, and if you're on a Blue Gene Q, you use run job. And if you're on an Argonne Blue Gene P, you use Cobalt MPI run, and okay, obviously it starts to get a little bit absurd. So what it means is, depending on your system, most likely a supercomputer, you have to read the manual or a web page or attempt to do it and then submit obnoxious support tickets or whatever about why it doesn't start. So, but just remember, so MPI exec should work great on hokey speed as far as I know, but it won't work on Cray or Blue Gene. And there's some magic. If you set up MPI correctly, you can actually ignore these. So how many of you know what PBS script is? You know when you do qsub? So when you do qsub, you say qsub file, and that file contains PBS and nodes 50, right? So the PBS knows how many nodes you're going to run on. So MPI can talk to PBS and get that information automatically, and that has sometimes that allows MPI to do a slightly better job how it lays out your processes and some things like that. So I don't know about OpenMPI, but Hydra has integration for like PBS and Slurm and Maui Moab, Cobalt, all the different resource managers. If you build it that way, the system interoperate the machine are almost certainly going to do that properly. If you build it yourself, like I do, I have to look it up and make sure I get it right. Otherwise, you have to pass in a host file. So this is like IP addresses, and it's annoying. So if you don't want to deal with host files, use the built-in MPI exec, and hopefully it's magic with PBS or something. So please verify this on hokey speed. One of the ways that you verify that something is wrong is if you use, like, if you say I'm going to run on 400 processes on 50 nodes, and your program runs infinitely slowly, and then you might log in interactively to that node and figure out that you actually launched 400 processes on one node and the other 49 nodes do nothing. That won't happen if MPI exec is smart, but that will happen if you don't know what you're doing and you don't pass in an MPI exec or a host file. So, almost done. Talk a little bit about performance characteristics, just to get a sense of what, so we can reason about what time this thing happens. So this, first of all, this is all in BGQ. BGQ is a weirdo system. Most other systems won't behave like this. But this is why you post all your non-blocking segments and do a wait all. Because you can actually, you don't have one network. You have one physical network in a global sense, but you have 10 network links coming out of every node. Each network link can do 2 gigabytes a second, in both directions. So if I am sending, if I'm doing neighbor exchange, of course in 5-dimensional space, doesn't really correspond to any physics. The lattice QCDs have 4D space. Most of the classical physics is 3D space. But if you're going to send in a whole bunch of directions at once, you drop those enqueue those messages, all of them, and then do await all, and you will see, okay, up here you're doing 10 links, and you're clipping along at, you know, I don't know, not 10 times, but a large fraction of 10 times the speed as you would on one link. And this is bumpy and not exactly perfect because I just wrote a pretty crude test. One of the guys at IBM who's a lot more thorough than I am has a perfectly smooth, you know, absolutely perfectly separated figure for this. But it's basically all the same. It's illustrative that more links equals more bandwidth. But if you do blocking send receive for each link, you will just get n of those. So good performance comes with non-blocking. So this is the Ohio State University micro benchmarks for MPI, just for reference. This is latency. So this is how much time it takes to send a message of this many bytes. So you can send a 1 byte message up to about a 64-byte message are all the same cost. That's funny, right? So it's sort of like a cache line. And you know, if you do a cache line is going to take you know, how many cycles to load, whether or not you use one element of it or all of the elements of that cache line, and that'll affect your performance. This is basically a packet size of 64 bytes. So you can send up to 64 bytes, and it's always one packet. So if you only put 1 byte in it, the packet still has to go. There's no 1 byte packet on any machine. It's not worthwhile to do. And then this is more for our bridging users, but with different compilers, it affects the software overhead. This has to do with the fact that we have a in-order processor. You will not see this behavior. MPI will behave almost exactly the same with GCC or LVM or Intel on an Intel system. And then you see, obviously, at 64, you hop up, latency goes up and up and up, and then it goes, you know, big messages, your bandwidth low. But this is sort of, you know, this is a pretty low number, right? So if this is under 2 microseconds, you can actually make this better. The network provided itself less than 1 microsecond. If you do send receive on a cluster that has InfiniBand, it'll be like Barbara said yesterday, maybe 5 microseconds plus or minus. If you do it on a 1 gigabit Ethernet network of workstations, it'll probably be, I don't know, 100 microseconds or more. Could be very, very slow. So this is internode and this is intranode. And here's what's funny. So watch the lines. So the lines go up when I use shared memory. So this is going across the network, and that's going across the DRAM bus. So part of this is because BGQ runs at a very, like half the clock speed, like 1.6 gigahertz, and has a really, really high-end embedded on the silicon network, and it actually is really balanced. You can actually push data across the network, in this case, basically faster than you can within node. And this is one reason why we want everybody on BGQ to use threads, because load store doesn't have this problem, but doing shared memory message passing does. And part of the reason is, so if I'm going to do send receive to a core on my node, I have one network. I've got the memory bus, and I'm going to do send, and the other process is going to do receive. So we're sharing the link. Whereas when I drop it into the network, I just hit a special piece of silicon and off it flies. So you only have to do half the work because the other side will do the other half. So there's that element to it. So this is bandwidth. This is a fairly nice but characteristic plot. So the bandwidth is a function of message size. So you go from 1 byte, and basically you see that the bandwidth improves. Of course, this is a log-log, but it's so the bandwidth improves linear on the log-log scale up until this is 64. So you hit the 1 packet. I think this is sending multiple messages as far as I know, and then it keeps going, and then it turns over at 8 or 16 kilobytes. We're at this is intranode, or internodes. This is bidirectional actually. So this is hitting peak bandwidth
at about 8K. That's somewhat anomalous. I don't think most networks hit peak bandwidth at 8K. One of the things that comes into play is BG doesn't have Linux pages. We don't have TLB misses and things like that, so you will see bumps at various, if you start doing large messages, you can see artifacts, larger messages from the TLB. So this is just intra-node. What happens out here, this little bump, if you happen to notice it, happens, of course, when you spill L2. So this is 1 million, 2 million, 4 million. So I can't remember exactly how I run the test. But basically, once you start computing to fit into L2 cache, your bandwidth drops down. Same behavior, all very smooth. Same here, bidirectional. So these are just sort of, don't use these numbers and make performance estimates on your laptop or on ODSP. But this is, but if you wipe out the axes, this is sort of an idealized network behavior. Maybe some of them will bend a little bit more sigmoidally.